The next kind of exchange reaction are called acid-base reactions. Acids and bases, it sounds dangerous, right? Not all acids and bases are dangerous. If you eat an orange, you're eating citric acid. Well, the stomach acid in your stomach is dangerous, but it's hydrochloric acid and you need it there. So what happens when you take an acid and react it with something called a base? You get water via an exchange reaction. A similar pattern to precipitation, but different product. Instead of making a precipitate, they all make water, one of the most stable compounds ever. Let's go talk acid-bases reactions. Crap. Nah, I'm keeping it. Let's go talk acid-base reactions. I screwed up. Well, howdy everybody, howdy. Welcome to another grammar lessons where numbers will take a break. At least the numbers that you will experience, you can count on one hand as we talk about more of the grammar of chemistry, and that is the special class of reactions, which is kind of like the second class of exchange reactions called acid-base reactions. So let's first talk about what is an acid and what's a base. An acid is an electrolyte. It produces ions, but specifically it produces an H+. So for example, the acid that's in your stomach acid is hydrochloric acid, and it will break into two ions. Now, not all acids break into two ions. They're just like ionic compounds. There's acids that have two H+ on it, and we'll run into one of those later. So H+ is what's produced along with Cl-, and notice that the charge on both sides is conserved. It's the same. Here's the acid in vinegar that's called acetic acid. Now you notice that I put a little double arrow there. Not all acids break up completely like ionic compounds do. So that's not really going to be the focus of what we're going to talk about today, because we're talking about the reaction of an acid with a base, and it doesn't matter if it's what we call a strong acid or a weak acid. All acids react with all bases. So a base produces the hydroxide ion in water. You might recognize the hydroxide ion from your solubility table. It's down there. Usually most hydroxides aren't very soluble, but remember the solubility rules. Sodium anything and ammonium anything is soluble in water. And so you'll see the difference here is that while acids make varying negative ions and always an H+, a base makes varying positive ions and always OH-. And so you see what happens here, or you don't have to see, you'll see in a little bit. If you react an acid with a base, you get water, because hey, look at this. What happens when you take one of these and you react it with one of these? H+, here, do this in your mind. H+ plus OH- goes to make HOH, which is water. And so every time an acid reacts with a base, you're going to get water and something else. And the something else is going to be some ions that either still are happy to be in solution and not precipitate, or once in a while you get a strange thing happen where the ionic compound produced will be a precipitate. Hey, enough talk. That's the background. Let's put it all into practice with an example problem. Here is the most common example problem you ever see. You take something as prevalent in nature as HCl, like I said, it's your stomach acid, and you take what's in oven cleaner, sodium hydroxide, which is sometimes called caustic soda. But once again, we have the three forms of the reaction. We got the molecular form. I just abbreviated with an M, an I, and an Ni. And now if you're not firm on molecular ionic and net ionic, go back and watch that precipitation reaction video again. But we're going to go ahead and we're going to bust. It's a little bit easier than an ionic than a precipitation reaction, because we're going to go ahead and say, hey, there's an acid. By the way, you always see an acid coming because the formula has an H on the left. So it's always H plus, and that's aqueous, and then something else minus. Now, you can say, well, the net charge is 0, so it's got to be a Cl minus, but you also recognize it's the same old Cl minus it's always been. And what you're going to make then with the base, it's going to make in solution Na plus and OH minus. Going a little faster because you're now well versed in how electrolytes break up. It's the opposite of what we did when we put them together and made formulas. So what's going to happen? Every time an H plus sees an OH minus, you are going to get water. And so in both forms, molecular and ionic, I'm going to go ahead and write an H2O. L, not AQ. So where precipitation reactions made a solid, this is going to make water liquid. And this is where we call they're neutralizing each other because water is neutral. Now the question is, what are the other ions going to do? They're going to be just happy to stay where they're at in solution, because if you go and look at what an Na plus and a Cl minus do when they hit each other in a solution or come into contact with each other, all sodium everything are soluble, and the only insoluble chlorides are silver, mercury, and lead. And so there will be spectator ions. The sodium and the chloride will be spectator ions. And the shorter way to write this would be NaCl, aqueous in the molecular form. Okay, net ionic, get rid of the spectators. Everything on the same side, or on opposite sides in the same form that underwent no change at all, are the spectator ions. So many a time, the net ionic equation of an acid-base reaction will boil down to H plus and OH minus coming together to make water. And that happens a great deal. Why does that happen a great deal? Water is one of the most stable compounds there is. And so nature prefers to kind of go downhill in energy. And if you got something that's less stable, it's going to become something more stable. Water is very stable. So in biology, you might see that a lot of the reactions, even in chemistry, a lot of the reactions, water's on the right. Dehydration synthesis, water's on the right. Making a protein out of amino acids, water's on the right. Combustion, water's on the right. Did I make my point? Probably too much. Let's do another one that's a little trickier. Ooh, tricky, tricky, tricky. Because what we got going on, folks, is we've got a situation where there are different, there's more than one H plus on a H2SO4, and so when that naturally breaks up, and I'm not going to write on this yet, I'll say if you were to do it on a little aside here, H2SO4, that makes 2H plus and an SO4 2 minus. What's an aluminum hydroxide make? Well, actually, I made that a solid. But you see it's got 3 OHs. And by the way, it don't matter if one of the participants is a solid. You treat it the same way. Just if 2 of them are solids, it's a little bit difficult. But this aluminum hydroxide used to be, it still is probably, in an antacid meant to neutralize acid, like your stomach acid, called rolaids. And it's just kind of potent because it's got 3 OHs on it. But do you see where we can't have 2 H pluses and 3 OHs can't happen? So this is where we start slinging coefficients, and you have to say, well, I need equal number of H pluses and OH minuses. And so you could look, that would make 3 OH minuses, or there are 3 OH minuses on it. This would produce in water 2 H pluses. And so after a little bit of a trial here, you would realize that I need 3 of those and 2 of those. And I sort of tried to show you that here, but I didn't want to mess up my nice clean looking reaction. So remember, the name of the game is equal parts H plus and OH minuses. And so you'll see that when I break this up now, you will get 6, because there's 2 on each acid molecule. You will get 6 H plus aqueous. And I will get 3 SO4 2 minus. Now let's just stop right there. The way you can check yourself before you wreck yourself. Plus 6, 3 times minus 2. That thing had a charge of 0. I just chose to represent it differently. And so 6 plus negative 6 is still 0. So if you got a net charge of 0 still, you know you're doing the right thing. By the way, you're probably familiar with aluminum. 2Al3 plus. And you know what I just did? I just kind of goofed a little bit. That's a solid. So this is going to stay the same. I started breaking it up into ions. So that's going to stay the same. I actually tricked myself with my tricky example. Still got OH minuses on it. Still going to make water. But how many waters? 6 H plus 6 OH minus is going to make 6 waters. 6 waters in both places, upstairs here in the molecular and down here. Now what's going to happen with the sulfate? The sulfate is just going to hang out there by itself, and you're going to end up having it be sort of lonely there by itself, and that's how that's going to roll. All right. And what about the aluminum? The aluminum is going to be liberated. I don't have enough room to write it. So that thing will dissolve. Whoops, sorry, I wrote off screen. And so what you'll have here is a way to write it in the ionic form. That's what you'll get. Remember, I've got negative 6, positive 6, still a net charge of 0. And if you were to write this in put this back together again to make it more concise, that would be Al2SO4 parentheses 3 aqueous. Can I write aqueous? Let's go check our solubility rules. Sulfate. Is aluminum an insoluble combination? No. So actually what will happen is, even though one of those is a solid, you will have the net effect of this will be that the solid will have dissolved, and it helped dissolve in the presence of the acid. However, who's a spectator ion? Sulfate. Is aluminum a spectator ion? No. It actually changed. So that changed on the left to the right. So you can't cancel aluminum. You certainly can't cancel the H plus. So now we just take everything that did not change. Remember, you're just kind of focusing on that. And we're writing it on each side. And then we could make sure it's balanced. And there's 2 ways to make sure it's balanced: in atoms and in charge. Now, it doesn't have to be the same in the net ionic. It doesn't have to be the charge of 0 on each side, but it has to be the same charge. And so if you just go count atoms, you got 6 H's. Now watch out. You got 3 H's. You got 12 H's, and you got 12 H's. And so then you've got 6 O's, and you got 6 O's, and you got 2 aluminums. If you look at the charge, there's a positive 6 on the left and a positive 6 on the right. So everything's balanced. It's just a kind of a strange example because unlike precipitation reactions, one of the things that's a component of an acid-base reaction can be a solid and the other can be an aqueous solution. And it does change the look of the net ionic equation a little bit. They don't all boil down to H plus OH minus is going to make water. So that was a little bit of a tricky one. Let's try one more that's going to be really weird. Not that weird, but it's going to be the same pattern, but just a little different. All right, still got sulfuric acid again. So let's go ahead and break that up. Here's the molecular form. Let's break that up into the ionic. And then we got a new base called barium hydroxide. And you know what? I'm not cheating, but barium hydroxide is what we call slightly soluble. And if you remember a couple videos ago, there are things that are slightly soluble. You can dissolve a decent amount of barium hydroxide, but if you look at the real simplified solubility rules, it would look like barium hydroxide is not soluble, but it's slightly soluble. So just kind of grant me a little bit of leeway here. Let's see if anything's different here. Well, it's going to make, let's see if the number of H pluses, now I kind of see it coming. There's 2 H pluses, 2 OH minuses. So I don't have the balancing issue I did in the last example. But let's go ahead and break this up. That's AQ. So I can break that up into barium 2 plus. Remember, barium's in group 2, so it makes a 2 plus. And then 2 OH minuses. Now, this is why I said this one's weird. This part isn't weird. H plus, 2 of them, is going to see that it's got, in solution, there's going to be 2 OH minuses. That's going to make 2 waters. And that's the molecular form too, because water is not an electrolyte. So we don't, right, that's not AQ, it's L. And now, why is this a weird one? A little bit weird, kind of not very common. Those two, according to the solubility rules, if you look at sulfate, sulfate precipitates with barium. So that's an insoluble combination, and that will make BaSO4 solid in both cases. So, very rarely, but in this case, what we've got going on is a combination of an acid-base reaction that makes water from the H pluses and from the OH minuses, but the leftover ions, remember that's the pattern of every single acid-base reaction is you got some compound. Those leftover ions precipitated. And so who are the spectator ions? Nothing. Ain't no spectator ions. And so the net ionic equation, I'm going to save a little bit of time. Same as above. Everything in the above equation is changing. The H pluses and the OH minuses change form into water. The barium and the sulfates precipitate. And so you've got a combination acid-base and precipitation reaction where you have various kinds of things that appear with these acid-base reactions in the net ionic equation. Quite often it's just acid making H pluses and base making OH minuses and producing water, like our first example with NaOH and HCl. But sometimes the leftover ions precipitate. So practice them all, and there's only so many different acids that are present, and they all have different negative ions And a lot of those negative ions are on this chart. And there's only so many bases, and a lot of the positive ions are on this chart because the ones that dissolve are going to be all your lithium, your sodium, potassium, ammonium hydroxides. And then once in a while you can have a base that doesn't dissolve very well, like an example we had with aluminum hydroxide. And so just practice them, folks. Go grab a book and do a bunch of different acid-base reactions and write them in all three forms. Next time, we'll talk about what happens when the ion charges change. That's called oxidation reduction reactions. So we'll see you then. Take care.